it's starting. All right, so let's start the lesson.
Okay.
So adding forces. Okay, so if forces are in the same line, okay, so that will make it very easy for you to find the resultant force or the net force. Now you can see here all three forces are in the same direction.
Okay, sir.
And they are in the same line of action, meaning they are in the same direction. Okay, so simply, very easy here. You directly add the forces here. 11 plus 7, 18 newtons. That is the resultant force. And here again, they are in the same line of action. Okay, so they are on the same line, but they are in opposite directions. So if they are in opposite directions, again, very easy. You again add them according to their direction. So this way 7 newtons, this way 11 newtons. So 11 minus 7 is 4 newtons.
Okay.
Okay. So the resultant is 4 newtons to the right.
Okay.
So if it is in the same line, it is very easy to find the resultant force if they have the same line of action, or if they are in the same acting in the same line. But if they are not in the same line of action, then it gets a little bit complicated. You know, for example, here adding perpendicular forces, again, it's quite simple when the two forces are perpendicular like this. Can you see here? 110 Newton this way, 70 Newton force this way. You can use the Pythagoras theorem and get the resultant. By the way, vectors are equal if they have the same size and the same direction. So even if the 70 Newton force was acting from here, all right, still if we have the same length and the same direction, then it is the same vector. So instead of drawing this vector here as 70 newtons, you can also draw it here, as long as it is the same length and the same direction. The length of a vector represents or is in proportion to the size of the vector. So here, if it is 70 newtons, you can take this as maybe 1 centimeter as 10 newtons. Then this should be 7 centimeters. This should be 11 centimeters. Okay? So if you are doing a scale drawing, and if you do it like this, you will realize that this will be 13 centimeters. You draw these two, take the scale as 1 centimeter, 10 newtons, then this will be 11 centimeters, this will be 7, and then this will be 13.
Okay. Sir,
Okay,
then
you
when
get the
do
correct
we
direction.
resolve, sir?
What?
When do we resolve, like, easy to find the resultant?
Yeah. So here, I mean, you don't need to do any resolving. You can directly use the Pythagoras theorem and get it, because the two forces or two vectors are perpendicular to each other.
Okay.
Okay? But if it is at an angle where they are not perpendicular, then you have to resolve perpendicular to one vector and parallel to the other to the same vector. Or else you can also use this rule of drawing the polygon and then finding the resultant. Okay, so for example, let's say you have two forces like this. You join the forces tip to tail. The tip of one vector connected to the tail of the other vector, and the gap here is filled by the resultant. Okay, again, when you're drawing the forces, you should have the same direction and the same size, and size of a vector is represented by its length. So you can move the vectors, you can translate the vectors, but they have to be the same direction and the same size. So for example, if this vector is like this, you can also draw it here like this, as long as it is the same length and the same direction. This vector, if you want, you can also draw it somewhere here like this. Okay, but remember, when we are using the polygon rule, we join the vectors tip to tail. So the tip of one vector joins the tail of the other vector. You see here, for this vector, the tail is here, and for this vector, the tip is here. So you join them tip to tail, and if there is a resultant, there will be a gap. You see here, from here to here, there is supposed to be a gap. The gap is filled by the resultant.
Okay, sir.
Okay, so you draw an arrow which joins the tip of one vector, the tail of one vector to the tip of the other vector, and that will be the filling the gap, and that is the resultant. Now earlier, do you see we join the tip to tail, but here when it's the resultant, we join tail to tail or tip to tip.
Tail to tail.
Tail to tail and tip to tip is joined when it is the resultant vector. You see here, this is the resultant vector, and here the tip of the resultant vector is joining the tip of the other vector. The tail of the resultant vector is joining the tail of the other vector.
Okay, sir.
Okay, and there is a video about this on my YouTube channel. If you subscribe to my YouTube channel, you can see one of the latest videos that I uploaded is explaining this.
So what's the name?
I think I sent that link to you.
Okay.
If I haven't, I'll send it to you later. Okay. So you can subscribe to that YouTube channel. I'm uploading lesson videos on it. Okay. So past paper question explanation. So many video. I mean, you can see the videos there. Which there were other students who had difficulties in past paper questions. So I created videos and uploaded them on YouTube.
Okay.
All right. So if you do a scale drawing, you join this tip to tail, then the resultant is this, and the direction is actually this direction, and the angle can give you also, you can give the direction in terms of the angle. Okay. So this many degrees of this force, but it has to be drawn correctly. So this is what we call scale drawing. Or else we can also use the, like I said, the polygon rule or the parallelogram. Now here it's actually the polygon you are using, because you see it's a triangle. You have two forces, so you can form a triangle where the third side is the resultant vector. Okay. You can also use something called the parallelogram rule. So these we are using when we are doing scale drawing. Do you see here what I said before? As long as the direction and the size are the same, you can move the vectors. Now you see here this vector is moved to this position in this diagram. Okay, so here we are not joining tip to tail because we are using a different rule. But if you are using that polygon rule, you join them tip to tail, the gap is filled by the resultant, but it's in the other direction. Now you see here these two forces are in the anti-clockwise direction. If you consider the inside of this triangle, these two are in the this one and this one, they are in the anti-clockwise direction, but the resultant is in the clockwise direction. Always the resultant force is opposite to the direction of the other forces. If the all the other forces, when you join them tip to tail, are in the anti-clockwise direction, the resultant force will be in the clockwise direction. Or if the other forces, when you join them tip to tail, are in the clockwise direction, the resultant force will be in the anti-clockwise direction. So it's always in the opposite direction, and you can see that here. Can you see it's joining tail to tail and tip to tip?
Yes, sir.
Okay. Okay. So another rule you can use is, again, scale drawing, is you can use the parallelogram rule. But again, you can apply this only when there are two forces. If you have several forces, you can't use the parallelogram rule. But you can use the polygon rule, which I mentioned. Okay, joining tip to tail and then the gap filling the resultant. If there was no gap, let's say when you join 3-4 forces, and if there was no gap, that means there is no resultant force. Okay, the object.
No gap means like.
So let's say you have the forces, you join them tip to tail, and then there is no gap left. That means there is no resultant force. Now here there is a resultant, that's why you have a gap here, and that gap is filled by the resultant. But if you join the forces tip to tail, all the forces that are given, and if there is no space for that gap, that means there is no resultant, because if there was a gap, the gap is filled by the resultant force, is joined by the resultant force. Okay, so this parallelogram rule we can use when there are two forces. Okay, so here we join the vectors like this, and in the middle what you get is the resultant. Okay, so here we have this force again, which you saw here. This force, that is that one, and then you have this, which is this one.
Yeah.
And you can see again, if it's a parallelogram, the opposite sides are equal, and also they are parallel. A parallelogram has opposite sides equal in length, and
they are parallel.
Yeah, and parallel. Okay, so here this and this should be parallel. Yeah, so that's how we form the parallelogram.
Okay.
All right, so this is how we form the parallelogram, and then these two ends are filled by the
Dotted line.
Yeah, the resultant.
Ah.
Okay, this is the resultant.
Okay.
Okay, then yeah, so if you measure this length or if you measure the angle, it will be the same as this one. Okay, it will be the same as this one. The length of the resultant here will be the same as the length of this resultant here. And again, if you measure this angle here, it will be the same size as this angle here, theta. And also you see here this angle here, 39 degrees. Now again, if you draw this vector from here, then that angle will also be 39 degrees. Do you see that? Because they have to be in the same direction, and this is, let's say, you can consider this as the horizontal. So then this will also be in the same direction. Any questions?
Sir, where will the other angle come? The 39 minus the other angle is
this angle here.
Yeah.
This angle here is equal to this angle here, theta.
Okay.
Okay, you have to measure it because this is done by scale drawing.
Okay.
You can use a protractor and measure the angle, and you will see that it is the same. Okay, then now if you can, another way is you can resolve the forces horizontally and vertically. Okay, so let's say now you know this angle here. The other way of doing it is by trigonometry. Okay, so then you don't need a scale drawing, you can get the exact value. All right, so what you do is you resolve this force in this direction. Okay, if you're resolving it in the parallel, in the direction of this one, then you cosine the angle. Do you remember that rule? So it will, if you take if you resolve this 400 Newton force in this direction, it will be 400 cosine 39. Okay,
So not sine.
Sine is in the opposite, in the other direction, perpendicular to this direction. So 400 sine 39 will be this. When you resolve this force in this direction.
So there are also questions, like in the same paper, you discussed in resolving. And for, like, I checked the marking scheme for up, they said it was sine, something like that.
But up, so up is sine. Now here, can you see? So if you are taking this side up, right? So 400 sine 39. This way is 400. Now this is the angle. So if it's sweeping the angle, then it is cosine. If it is not sweeping the angle, and if it's perpendicular to this side, then it is sine. You see here, this 400 Newton force is sweeping this angle to get resolved to this side.
Okay.
So then it will be 400 sine 39. If it is perpendicular to this side, it will be 400 sine 39. This side will be 400 cosine 39.
Okay.
Okay.
So can you, like, just check that for?
Yeah, we can do that now. There are some questions. Yeah, so here we have, it's the next step. Okay, we can actually do that here. Okay, so let's say you want to find the resultant here. Okay, I will do it on this. Okay, so let's say you have this force. Now we will now do it by trigonometry. Okay, so here we have one force this way, which is which is 450 newtons. And then we have another force which is a bit lesser. So I have to draw the length a little bit lesser than this length because it is lesser, 400 newtons. Okay. If I am using the parallelogram rule, what I do is I draw something that is equal in length to this and parallel to this. Okay. So I draw the dashed line equal in length to this side and parallel to this side. That is if I am using the parallelogram rule. Okay. And then this length here should be the same length which I should draw here, and also it should be parallel to this. Okay, so something like this. Okay, so that's how you form the parallelogram, and the resultant will be joining the two ends of the parallelogram. So that will be the resultant.
Okay.
Okay. So from here, this end to this end, that will be the resultant. Now that is if you are using the parallelogram rule. Now if you are using trigonometry, now earlier when you saw that when they are perpendicular, it's very easy to do the question. Okay, so directly you can get. But if it is like this at an angle, okay, what you have to do is resolve it perpendicular to one direction and parallel to again that direction. So again, if I draw this like this, let's say this is the 450 Newton force and this is the 400 Newton force. Okay, so what I do is I have to resolve this in this direction. So if I resolve it, you can imagine that there is a light shining from here. Okay, imagine there is a light shining vertically from here. Okay, then right above this. So then the shadow will be here like this. Do you understand that?
Yeah.
The shadow of this will be right below it like this. Okay.
Yes.
And also they had given us the angle. The angle was 39 degrees. Okay, so here the angle is 39 degrees. I'll label that also. 39 degrees. Okay, now this is very simple. You are using simple trigonometry. Okay, so this length will then be 400 cosine 39 degrees. Okay, so the full force in this direction, if you consider, is 400 cosine 39 plus 450. Now again, you know, in the O-level class you learn trigonometry. Okay, so if you have a triangle, a right angle triangle. Okay, so here also this is a right angle. Okay, this angle here is 90 degrees. So if you have a right angle triangle like this, let's say, and let's say you know this side, the hypotenuse, and let's say you know this angle theta, then if you want the adjacent in terms of the hypotenuse, so this is the adjacent side, this is the opposite side. Okay, so if you want the adjacent side, now with these two, so what do? We do cosine, right? Cosine theta is equal to adjacent over hypotenuse. So the adjacent side in terms of the hypotenuse is h cosine theta. Can you understand that now?
Yeah.
So this side is 400. So this is the adjacent side of the triangle. So then that will be what? The hypotenuse cosine the angle between the two sides. So that's how you get that. If you want to find the opposite side in terms of the hypotenuse, we use sine theta is equal to opposite over hypotenuse. So the opposite side in terms of the hypotenuse will be h sine theta. Okay, so again, if you draw the other side of this, that means again you can imagine there is a light shining from this side. Okay, so let's say there is a torch, there is a light shining from this side. Okay, then what will be the shadow on this side? Something like that, right? Right, like that. Do you understand this one now? Okay,
Yes,
so this side will be what? 400 sine 39. Can you understand this? This is now, if you consider again this triangle, this side and this side are equal in length. Okay, so in this triangle we found this side, the opposite side. So this is the opposite side in terms of the hypotenuse. Opposite side, this side in terms of the hypotenuse is hypotenuse sine theta. So the hypotenuse is 400 sine theta, and this length are equal.
yes. So should we use that 39 degree or the one above, like 51 degree?
No, now see, it is this angle, right? This triangle. So for this triangle, which angle are you using for this side? This angle.
39. Okay.
Yeah. So you have to use this. Easy way to remember it is like this. Let's say you have this side, and if it is sweeping the angle, now do you see, to go from here to here to get this one? So you are going, you see, you have this, and you are going this way, right, to get this side. You are sweeping the angle. You are going through the angle. Can you see this side? So then it is cosine. If it's then the other side, it is sine. If it's not sweeping the angle, it is sine. If it is sweeping the angle, then it is cosine. You know, so you understand what I mean by sweeping?
So I mean going and
it's okay. Imagine there is a thread here. Okay, thread here that is fixed here, and then the thread length is this one. Then if I move this down, what happens? The thread passes through this angle to this side.
Yeah.
So it's passing through, it's sweeping the angle, then it is cosine. Okay, here it is not sweeping this angle. When again, imagine the thread is here like this, you move it to this side. Is it passing this angle?
No.
No. So that's why it is sine. You can remember it that way.
No, sir, I'm asking if we use 51, is it wrong, sir? Like.
Okay, now look. Try it with this. Okay, so now we have this one, right? So now I'm going this way. Can you see it swept the angle when I came here?
Yeah.
39 degrees. Okay. So then if it's sweeping the angle, I have to use cosine. Now if you go this way, is it sweeping this angle? No.
No.
So then we use sine. But if the angle was on this side, let's say this angle, so it is what, 90 minus 39?
51.
51. Okay. So if you use that angle and resolve this way, then this will be okay. So if you use this angle, this is how much? 59. 51, right? 51 degrees. Okay, so if I use this angle, then this will be, again, now if you use this side, it is sweeping the angle, right? If you use this angle, so then it will be 400 cosine 59 degrees. Okay, because it is sweeping the angle. 400 cosine 59 degrees. 51 degrees, sorry. 51
Sir,
degrees.
you get the same answer, right?
Yes. Okay, now again look, it is sweeping the angle, right? again, if I use this here, now can you see when I got it this way, it swept the angle. So then if it's sweeping this angle, then you have to use cosine.
Okay.
So the other side will be what?
Sine.
Yeah, sine 51. Okay, so here I can write this is equal to 400 sine 51 degrees. And if you use the calculator and do this, 400 cosine 39 is equal to 400 sine 51. Same way here, 400 sine 39 is equal to 400 cosine 51.
Yes. So it should sweep the angle and that's it.
Yeah.
Okay.
Okay. I mean, you can even try it with this triangle. Now, if you consider this triangle, okay, this triangle here, this angle is 51 degrees, right? So we can take it as theta. Okay, so this is the angle for this triangle here. Okay, so let's say this is theta, then this angle is 90 degrees. Can you see that here it is 90? Yes. Then if you do the same thing, then this will be the adjacent side. This is the opposite side to the angle, so opposite. This is the hypotenuse. Then same, you will get the same thing. Okay, so then again the same thing, right? Sine is what? Opposite over hypotenuse. So then the opposite side, this side, which is equal to this side in length. Okay, so if you consider this triangle, this side and this side are the same length. Okay, so if you consider this triangle, then the opposite side is what? H sine theta. The hypotenuse is 400 sine 51. This side. Can you see 400 sine 51?
Okay.
Okay, the other side same thing. Okay, so easy way to remember is if it sweeps the angle, then it is cosine of that angle. If it doesn't sweep and if it is perpendicular to the other side, then it is sine. Okay.
Okay.
Okay, then now we are not done with this question. So we have to find the resultant now. Okay. So then what we will get is something like this. Okay, so if you consider this one, okay, I will write it somewhere down. Okay, so what we will get is for this thing, you will get this way. The total force, I mean, when you resolve in this direction, the total force is 450 plus what? 400 cosine 39. We can use either value. Okay, we can also use 400 sine 51. So I'll use 400 cosine 39 because that is what I used in the beginning. Okay, so either one you can use, no problem. So 400 cosine 39. Okay, then this way, what is the total force when you resolve? What you have here, because this 450 Newton has no effect. Okay, when you cosine 90, it has no effect. So say this way. So here it is 400
sine 39.
Yeah, 400 sine 39.
So ask 450, sir.
450 this force, the original force, this one. Because this one we resolved this direction. This
so
was already there.
We should add it.
Yes. So this is already there. Then this thing only you resolve in this direction.
Okay.
Now this, if you take cosine 90, 450 cosine 90, that is 0 because cosine 90 is 0. So this 450 Newton force has no effect in this direction, perpendicular direction to it. So here we have what? 400 sine 39 degrees. Okay, now you can see we can use the Pythagoras theorem here. Okay, so again I can draw a rectangle. Okay, so
So
now you
aren't we adding 400 for that this thing?
this side.
Yeah, vertical.
No, because the 400 Newton force is this way. It is perpendicular to this direction. When it is perpendicular, it doesn't have any effect. Can you push something by applying a force perpendicular to the floor?
No, okay.
Do you get it?
Yeah.
So when it is perpendicular, it has no effect. So it's like trying to push something on the floor by pushing it down. If you apply the force vertically to something that is horizontal, then you can't move that object by applying a vertical force.
Yeah.
Force has to be at an angle. The best effect is when it is horizontal.
Okay.
So here we have this one. Now the resultant is in this direction. Okay, the resultant is in this direction, and you can see this side and this side, they are equal, and the angle here also 90. So we can find the hypotenuse of this triangle. The third side using the Pythagoras theorem. Okay, so the resultant force, let's say I call it R. R is equal to square root of 400 sine 39 squared, 39 degrees whole thing squared, plus 450, no, again this whole thing is in brackets, plus 400 cosine 39 degrees whole thing squared. Okay, so whole thing then after the square root. All right, now that will give you the size of the resultant force. You also have to find the direction. So to get the direction, you can find this angle here. Let's call it the
trigonometry.
Yes, so that will be what? Tan. Yeah, so tan theta equals this side, right? That is 400 sine 39. 400 sine 39 divided by this value here. Okay, so since I don't have space, I will just draw an arrow. Okay, everything here under that. Yeah. And then to find the angle, you take the tan inverse, shift tan of this result. Okay, you know how to do it, right?
Yes.
Okay. Then, yeah, so that's how you do the vector question. All right, then yeah, so that's how you do it. You can also do it by scale drawing, all right, like this, and measure it and do it. Okay, so the resultant of these two, you know how to do, use the Pythagoras theorem, and to find the angle, again you can draw that rectangle like what I did here in the example, and then get the angle there.
Okay.
So answer all these questions, okay, and the definitions are important. A free body force diagram or free body diagram of an object has the object isolated, and all the forces that act on it are drawn in at the point where they act, using arrows to represent the forces. So when you draw a free body force diagram, you draw only the forces acting on that particular body. If it is a free body force diagram for that particular body, again you draw only the forces acting on that body only. You don't.
So that means only the resultant force.
No. you draw, in the free body force diagram, you don't draw any resultant forces. In the free body force diagram, you draw only the forces acting on that particular body.
Okay.
That is what you call a free body force diagram.
Right.
So for example, for a person standing on the ground, there are two forces acting. His weight is acting on him, and the reaction force or the normal contact force exerted by the ground on him is also acting on him. So you draw only the forces acting on a particular body if you want to draw the free body force diagram for that body. Let's say take another example. Let's consider there is an object that is sliding down on a friction rough surface. Okay, so this is the rough surface inclined. Okay, the rough surface inclined, an inclined rough surface, and let's say I have a block on this surface, and this block is sliding down this surface. Okay, so this is the block and it is sliding down this surface. Now if I want to draw the free body force diagram, what I told you, you draw only the forces acting on this particular body. So FBFD, free body force diagram, in short also we say free body diagram, or long word is free body force diagram. So we draw only the forces acting on this body. That will be the free body force diagram for this. So what the one force is, what the frictional force. Okay, so the frictional force we can say is this way. Since it is sliding down, the frictional force is always opposite to the direction in which the object is moving. Okay, so let's say this is moving down. Okay, this is the direction it is moving. So the frictional force is this way. So this is one force. Then the other force is what? The weight. Okay, so the weight is acting vertically downwards on this. So both of these forces are acting on this body. Then let's say there's another force. What is that? The normal contact force. Okay, the normal contact force is the force exerted by the surface on the body. Always the normal contact force is perpendicular to the surface it is exerted from. And the frictional force, if it is between two surfaces, it is always parallel to the surface, to the two surfaces. Frictional force is always parallel. The normal contact force is always perpendicular. So I can also draw a 90-degree angle here to indicate that it is perpendicular. And what about the weight force? The weight force is always vertically downwards.
So when we are calculating work done, should we calculate it the distance from down to top or the distance moved?
Work done is force into distance moved in the direction of the force.
So like a same problem like this is in the paper like which we discussed.
Okay. Okay, so what I wanted to explain to you was the free body force diagram. Okay, so now these are the only forces acting on this body which is sliding down. The frictional force, the normal contact force, and the weight force. This arrow should be vertical. Okay, I try to draw it vertically, but okay. So here it should be quite vertical, and it should not be curved like this.
No, that's
you know, it's a vertical because force arrows, the force arrows should not be curved. Okay, it has to be something like let's say it has to be a straight line. You can't have vectors which are curved. All the vectors should be straight lines.
Right.
Yes, straight arrows, not curved arrows. Okay, so we have the weight force which is vertically down towards the center of the earth, the frictional force which is always perpendicular to the surface it is exerted from, and then we have the frictional force which is always parallel to the two surfaces that cause the frictional force. Any questions?
No, sir.
Okay, so these definitions are important. Okay, so what was your question then? That is the end of forces. Then the next chapter is moments.
So that the paper which we previously discussed, sir, not that, sir. Basic.
Yeah. Was it this one or the one before? But the other one was about this one, right?
Yeah, this thing.
Okay. Let me take the answer. During the 17th century, the physicist Galileo carried out a series of experiments to investigate how gravity affected acceleration. There were no accurate methods to measure short times, so Galileo used an object on a smooth inclined plane to increase the time taken for the object's motion. Okay, so there were no accurate methods to measure short time, so Galileo used an object on a smooth inclined plane to increase the time taken for the object's motion. Okay, an object is released from rest and slides down a distance s and slides a distance s. You can see that here. A smooth slope, a smooth incline. Smooth means there is no friction. Okay, so we assume there is no friction here between the two surfaces. That is the block surface and the inclined surface. And it is released from rest and slides down a distance s down a smooth inclined plane as shown in diagram 1. This will take longer than releasing the object from rest and allowing it to fall freely through the same distance s. Okay, so the time taken for this object to go from here to here is longer than the time it takes for this to go from here to here.
Yeah, sir.
That's what they say in the question. This will take longer than releasing
How are they
the
measuring the time, sir?
What?
How are they measuring the time, sir?
No, why do you want to know that? They have not asked you anything about it. They can use a stopwatch, they can use a light gate connected to a timer. There are so many methods. Okay. Okay, so the question is asking, assuming the frictional forces between the plane and the object are negligible, explain why the object in diagram 1 takes longer to travel distance s than the object in diagram 2. Okay, so here you see it is moving at an angle this way, but there it is falling vertically. Now there is only one force acting on both objects, because here I told you okay, there are actually two forces here, that is the normal contact force and the weight.
Yeah.
Here, assuming no frictional forces, so actually there will be friction, but we assume there is no friction here, and also no frictional or air resistance here. So on this, the only force that is acting is the weight.
Yeah. Okay.
Here you have weight and also you have the normal contact force. Okay, so the normal contact force is acting perpendicular to the plane, to inclined plane, because it is exerted from this surface. Always the frictional forces are perpendicular to the surfaces they are exerted from. Okay, this way. Then the component of the weight, now the weight is vertically downwards, and if you take the component of the weight perpendicular to the plane, that is in this direction, it is balancing the normal contact force, because there is no motion of this object in this direction. Okay, all right. Yeah, so the component of the weight down the plane is what moves this object down the plane. Okay, so there are two components. One is parallel to the plane, which moves the object down the plane, and then there is another component of weight which is perpendicular to the plane, and that component balances the normal contact force so that the object will not move perpendicular to the plane. The object moves only parallel to the plane. You see in this part, it is the component of the weight that is down, and the component means it is a lesser value than the original force because it's a component, part of the force. All right, like I showed you in the previous example where you imagine the shadow falling on the object. Okay, so similarly on this, in this direction, it will be a component of the force, meaning it is part of the force that is acting in the direction it is moving, but here the full force is acting. Okay, so here the acceleration is down the plane, here it is vertically downward. So here down the plane you get a lesser force to cause the acceleration. Okay, but in the other example the size of the force is vertically downwards, which is again in the direction. So in the second case, the force is in the diagram on the left, the force is less, which is causing the acceleration. So you know F is equal to ma Newton's second law equation. The mass is the same in both cases. Okay, so here the force is a component of that weight force, so the force here is less. Okay, so the force here is less, but the force here is actually the original force, so it has its actual maximum value. Okay, but here in this case the force will be less. So the force here will be less, therefore the acceleration will be less.
So why will be the force be less?
Because it's a component of the force down the plane. The weight force, we are taking a component of the weight force. Okay, so even if you consider here, if I draw this diagram here now, in this one there is no friction, but if you can take the component of the force, so one component is this way, okay, which is balancing the weight force. Okay, so if you do W cosine theta, that will be equal to N. Then the other component of the weight is down the plane. Okay, so that way this will be W sine theta, the component of the weight force in this direction. Okay, the component of the weight force in this direction, the component, all right, will be W cosine theta. So both are components. So the component of the weight in this direction and the component of the weight in this direction, both will be less than the actual weight force. Okay, so this will be equal in size to this because there is no motion of the block in the perpendicular direction, but there is motion of the block in the direction parallel or down the plane, and what is causing that is the component of the weight. So it just slides down. Okay, but you know this weight is less, a weight component is less compared to the actual weight, and this is actually the result. In this example there is no friction. Okay, so this friction is not there, so the only force is the component of the weight down the plane, and that is less compared to this weight force here. So we are comparing the component of the weight here with the actual weight. So here you have the actual weight acting downwards, here you have only a component of the weight acting down the plane. Okay, so that means the result, now here the resultant force is the weight, here the resultant force is a part of the weight.
Component.
Part of the weight means less than the actual weight, so that means the resultant force here will be less, so therefore the acceleration will be less here. Here you get the acceleration due to the weight, which is 9.81. So since the acceleration here is less compared to the acceleration here, it will take a longer time, because greater the acceleration, the faster it moves.
Yes.
Let's check the answer. So this computer has become very slow. Okay, so you see here, that's what they're saying. So resultant force is W. That is for diagram 2. What I told you. For diagram 2, the resultant force is
Weight.
W.
Yeah.
The weight, the actual weight. Or the acceleration is G, because W equals mg. So in this one, the resultant force is the weight. Okay. In this one, the resultant force is the weight. So F is equal to W in this one. So acceleration will be then G, because W equals mg. The weight force causing the acceleration gives acceleration of G. Okay, so that's what they mean. Then diagram 1, the resultant force is the component of the weight, part of the weight, which we say the component of the weight along the plane. Along the plane means in this case down the plane, or see a reference to this thing. So this you get when you resolve the force. Okay, the force down the plane. Okay, if I resolve it, this is what W equals mg. This W equals
mg.
Okay, so this is what then mg sine theta. It's a component of the weight. This is mg sine theta. Okay.
Yeah.
Or we can say acceleration. Now W, so mg. So this is what acceleration is g sine theta. Okay, because F is equal to ma. All right. So the resultant force is ma. Write that here. So if you consider this, then it is what ma. The resultant force is ma and is equal to what? This is what mg sine theta. Mg sine theta. And what happens? The m's cancel out. So you get A equals, the acceleration down the plane is g sine theta. Okay, assuming this frictional force is 0. Okay, no friction here. And then in that question there is no friction. That's why. Okay, so you get, that's how they get g sine theta. Either one they allow. Okay, A equals g sine theta. This can be inferred from a diagram. Then a comparison, 1 mark for writing this, 1 mark for this, any of this, and then another mark, a comparison between either mg sine theta or g sine theta and mg, or g leading to a small acceleration in diagram 1. Okay, because it's the component of the weight down the plane. In diagram 1, the force, the resultant force down the plane is much less compared to the resultant force in this, which is vertically downward. So here it will cause a small acceleration than in this one. See, that's why they say a comparison between mg sine theta, that is the component of the weight down the force, or g sine theta, and mg. Mg is the weight force which is on that object which is dropped vertically. So in the other one you have what? There is an object. You have an object that is just dropped to the ground. Okay, so the force of this is W. So here the resultant force is what? Is equal to W, which is equal to mg. Okay. So the object that is dropped, the force is mg, but the object that is sliding, the resultant force is mg sine theta. Okay. Yeah. So that's why, because mg sine theta is less than mg, you get a lesser force and therefore a lesser acceleration. Any questions?
No, sir.
Okay, then the next part of that question. Calculate the acceleration of the object in diagram 1 when theta is equal to 35 degrees. Now they say this angle is 35 degrees. So similarly, actually this angle here is equal to the angle there. Okay, so this angle is equal to theta. Okay, this angle and this angle, they are equal. Here also you have theta. Okay, because this is a right angle. So if you consider this big triangle,
Yeah.
okay, if you consider the big triangle, if you consider this triangle here, this angle is 90. So this angle will be 90 minus this, or 180 minus 90 minus this. Okay, that will be this angle. Or we can say, because this is 90, this plus this is 90, right?
Yeah.
So here we can say the angle here is 90 minus theta.
Yeah. Okay.
Okay. Then again, to get this angle, what are you doing? Again, this whole thing is 90 from here to here. Again, what you are doing? 90 minus this angle, which will be equal to again this one. Okay. That's why this angle is equal to this one.
Yes.
Okay. So now we are supposed to find the acceleration of the object when theta is equal to 35 degrees. So what we'll do is, now we already have the equation, that is w sine theta, and already they gave us this angle theta. So we can find the acceleration. So acceleration is what? G sine theta. You see this? Yeah, so it's 9.81 sine 35 degrees. See? 9.81 sine 35 degrees, which is 5.61 meters per second squared. Okay?
Okay.
Yeah. Any other questions then?
No, sir, that's it, sir.
Okay. You sent me something, right?
Yes, sir, that's by accident, sir. Sorry, sir.
Oh.
So then, okay, right.
All right. Then wait, I'll send this lesson to you. I mean, the slides, what I wrote, you can send it to you. So today we did vectors and did we do vectors? Basically vectors, right? Vectors.
Yes.
The computer has become really slow. I'm wondering what happened. So it's not responding.